All right, welcome to Chapter 9 lecture, the intro. I'm going to introduce alcohols, ethers, and oxides, thiols, and we'll get started here in a second. Oops. Okay, so this is Chapter 9. Start with 9.1, Introduction. Okay. In this case, there's not a lot of new mechanisms, but there's a lot of variants on the mechanisms, and you have to know essentially every mechanism we cover, you need to know. So we have alcohols, ROH, ethers, ROR, epoxides, which is a cyclic ether. We have different R groups here. It's a cyclic ether. There's ring strains, very special cyclic ether. There is ring strain that allows us to do some interesting things with epoxides. And then there's thiols and sulfides, okay, the sulfur analogs. There is a sulfur analog for the epoxide, but we're not so worried about that. So recall that we classified carbons, hydrogens, and then we classified alkyl halides. So we can do the exact same thing with alcohols. Primary alcohol, secondary alcohol, and tertiary alcohol. P3 hybridized all the way through. That's going to be important. We're going to see very similar reactions. We're going to actually see the opposite reaction of what we've seen in the alkyl halides. Just like we did with the alkyl halides, there are some OHs that we're not talking about. We're talking about sp3 hybridized, not sp2. That's an enol, is what it's called. And this is called a phenol. It's a special alcohol. It's an sp2. It's an aromatic alcohol. So neither of these are going to undergo the reactions we're talking about. With ethers, you can have symmetrical or unsymmetrical. So you can have the same group. We've introduced diethyl ether. You can have unsymmetrical ethers, and you can have epoxides that can vary in substitution. Okay, so that's just an intro. 9.2 is structure and bonding. Is the name of this one. Okay, so we've introduced this already. Alcohols have some very special properties, just like similar to water in some cases. Like water, they're sp3 hybridized at oxygen. There's a delta minus on the oxygen because it's electronegative. There's a delta plus on the H and a delta plus on the carbon. That oxygen's sp3 hybridized. The bond angle is about 109.5. It's tetrahedral. Okay. This H constitutes a major difference between alcohols and ethers. Ethers do not have the capability of hydrogen bonding because they don't have a hydrogen bound to oxygen. So that's a big, big difference. Okay, still have partial plus charges, still have partial minus, but no hydrogen bonding. It's a big difference. Whereas epoxides, as we mentioned, have ring strain. This bond angle is 60 degrees instead of 109. Still sp3 hybridized on the oxygen. And you can have different groups. I'm just drawing hydrogens right here. This is ethylene oxide, very useful compound, but that's epoxides. Okay. 9.3 is nomenclature. One thing before we move on, again, hydrogen bonding. That's a key thing with alcohols. Okay, hydrogen bonding. 9.3 is nomenclature. We'll look at some common names and some systematic names, which we call IUPAC. So a few common names that I want you to learn because they're going to reinforce these I'm sorry, they're going to reinforce these substituents. Isopropyl alcohol. It's going to reinforce that that's an isopropyl group, isopropyl alcohol. Isobutyl alcohol. Sec-butyl alcohol. Okay. And then tert-butyl alcohol, or T-butyl alcohol. Okay. Just like the common names for the alkyl halides, they're more common. That's what we use much more commonly. Okay. Systematically, we have methanol. I'm going to have you learn 1 through 8. Ethanol. I want you to name these. Propanol. I'll give them to you verbally. Butanol. Again, these are the normal, the straight chain versions. Okay. So methanol, ethanol, propanol, butanol, all the way to octanol. Okay, so 1 through 8. That's going to be our theme. So let's do some IUPAC naming when we have some substituents. The key thing here is the OH takes priority. Okay, for alkyl groups and halides, halides were no higher in priority than alkyl groups, so it's simply the lowest numbered substituent. Alcohols, however, are going to take priority, and so it may be that the alcohol has a higher number than another substituent, but that's going to take priority. Okay, so let's look at a few. As always, we're going to find the parent. The alcohol takes priority, so the alcohol is at the 1 position. Pentane is the parent. Drop the ane, add all, so it's a pentanol. And there's 2 methyl groups at the 3 position, so it's 3,3-dimethyl, 1-pentanol. There's always a couple different ways to do these names. I'm going to stick with one and try to be consistent. Okay, but there's sometimes there's other ways. And sometimes you see the all broken up in between the word. Okay, I like this way where the 1 is before. Sometimes you see pentan 1 all. I like 1-pentanol. Okay, the other way is not incorrect, but I'm going to teach it this way and try to be consistent. So let's look at another example. I have this in my notes. It's actually a nonane. That's a 9, but we're going to use it for teaching. I said you have to go to 8. So okay. But you got a nonane is your parent. Alcohol's at the 3 position. Group at the over here, like at 8. You circle 8, even though I'm not putting anything there. If there was a methyl group there, it wouldn't matter. Okay, the alcohol would take priority. It's the lowest number you can have the alcohol be is what you need to have. So here, what do we have? We got an isopropyl at 5, and we got a methyl at 6. And so alphabetically, isopropyl comes before methyl, isopropyl, 6-methyl, 3-nonanol. It's a funny word. Okay. There'd be a dash there. 5-isopropyl, 6-methyl, 3-nonanol. Okay. Let's do a ring. It's cis. That always comes first. It's a cyclohexane derived. There is no 1 because it's assumed that the alcohol has to be the 1. Then you name the tert-butyl. So it's cis-2-T-butyl cyclohexanol. Okay, you don't need the number for that. All right, a couple diols and triols. I don't want to make a big deal about this, so I'm going to say we won't do systematic naming of diols and triols, but I want to give you a couple so you see them. It's just so this is just 1,2 ethane diol. This is 1,3 propane diol. We'll see diols from time to time, so it's good to mention them. Okay, you can have a triol, etc. You could have a trans or a cis cyclopentane diol. Okay, but we're not going to do any systematic naming. Ethers. Let's look at these. Symmetrical are pretty straightforward. Symmetrical, very common one. We've seen diethyl ether. Diethyl ether. Same idea. We're going to do 1 through 8. Okay, dimethyl, diethyl, dipropyl, dibutyl, etc. Up to dioctyl. Okay, so do 1 through 8 of the symmetricals. Now, unsymmetrical are, all you have to do is name each half. Okay, so what's that mean? Let's do a couple. We got a methyl and we have a sec-butyl. So it's sec-butyl methyl ether. Again, any combination of 1 through 8. Once you learn the rules, it's not that bad. That's a tert-butyl poorly drawn. That's tert or T-butyl ethyl ether. Okay, just space between ethyl and ether, but no big deal. Butyl comes before ethyl. Okay. Now, some common alkyl groups that you need to know, because this is how we're going to name branched ethers. Okay, so this is CH3O bound to something is methoxy. Okay, same thing. It's methoxy, ethoxy, propoxy. Okay, oxy at the end. You drop the ane and you add oxy. So instead of methane, it's methoxy. And it's an O minus with a sodium. It's methoxide. Okay, so you see some repetition. Okay, again, all the common ones, right? Isopropoxy, isopropoxy, tert-butoxy. Okay, so go through all those. Drop ane, add oxy. So now when we branch, the reason these are valuable, let's do an example. There's a 7-membered ring with an O, CH2, CH3. Okay, we can't name this 1, 2, 3, 4, 5, 6, 7. Whoops. Scratch that. Should be 7. My fault. 1, 2, 3, 4, 5, 6, 7. Okay, so 7 carbons. At the 3 position is an O, CH2, CH3. This group branched is uncommon. There's no common name for that. So it can't be ethyl, sec heptoxy or something like that. It's 3-ethoxy heptane. 3-ethoxy heptane. Okay, this is the IUPAC. We use common names when we can. A straight chain up to 8, or one of the 4 that we learned: isopropyl, sec-butyl, tert-butyl, etc. All right. So let's do a ring. Okay, again, there are sometimes multiple options. This is acceptable, is methoxy cyclohexane. I think the best way to name it is cyclohexyl methyl ether. Okay, so if we can use common names, it's good because we know what in the common names we're teaching. Okay, so I'm making it a point which common names you need to know. Okay, here's a common name that you don't need to know because it's not, even though they're these other common names, they're I don't know, intuitive. This is just called tetrahydrofuran. I just want to introduce it as a cyclic ether. You don't need to worry about the name. We call it THF. It's a nice solvent, so you might see that from time to time. You don't need to know that name. Okay. Epoxides, for naming, we're only going to do one way. We're going to name them as 1,2-epoxy something. Okay. So let's do this ring 1,2-epoxy cyclohexane. Okay, so cyclohexane is the parent. Epoxides by definition are 1,2. We just name them 1,2. Now, if there's a substituent, that's why the 1,2 is important. Okay, so 1,2-epoxy cyclohexane. Let's do another one. We can use the cis and trans language that we've been using. We've got a 1, 2, 3, 4, 5. We have a pentane. Got an epoxide on that pentane. It's cis 2, 3, because the epoxide takes up 2 carbons, 2, 3, epoxy pentane. You got to have 2 numbers for epoxides. As always, practice these things, and you'll get better and better at them. Okay, 9.4 is physical properties. As always, we sort of just mention these, and then when it comes time to explaining something, we'll mention them again. Okay, so there's hydrogen bonding with alcohols, and there's dipole-dipole interactions with ether and epoxides. Epoxides have ring strain as well. 9.5 is interesting alcohols, ethers, and epoxides. Okay, we're going to skip lecturing about that. 9.6 is prep. As we'll do often is we'll introduce a functional group. We'll talk about how to prepare these things, and then we'll talk about the reactions of them. And the preparation serves as review. Okay, so let's go ahead and go back over. Let's give you an example. This is ethyl bromide. What can you do with alkyl halides? We'll leave off all the lone pairs. On the oxygens. Lots of different variants on the same theme, right? Sodium hydroxide, SN2. All of these are SN2 because this is a primary, so this is some good review. Gives alcohol. This sodium acetate, this is the nucleophile we talked about at the beginning, was our kind of a teaching nucleophile. It's a moderate nucleophile because it's resonance stabilized. It's not as strong as OH minus or OCH3 minus, okay? But it still is going to go SN1 because we have a primary alkyl bromide. Ester, this is an alcohol. What do we get over here? We get a couple ethers. This is our diethyl ether, very common. This is a famous reaction, the Williamson ether synthesis. Okay, so we make an ether, symmetrical. Here, we make an unsymmetrical ether. Methyl ethyl, or rather ethyl methyl. Okay. Ethyl methyl ether. All right. So let's look at a synthesis problem. Okay, remember we said organic synthesis is retrosynthesis is working backwards. So here we have a question, how would we make this? That's what a retrosynthesis problem is fundamentally asking. Here, there are two possibilities, actually. With an ether, there are two possibilities. You can disconnect. We call this a disconnection. You can break. This is all mental in your head. If I asked you how to make this, you would look and you'd say, I think you could make an ether in principle by either bond. You could make either carbon-oxygen bond. So let's look at pathway A. When you break it apart, you're going to think, what's the most logical thing to have a plus charge, and what's the most logical thing to have a minus charge? And you think of it as, these are called synthons. They're not real thing. They're imaginary synthetic intermediates. Okay? But you might say, and what you're doing is just polarizing this bond. Because the oxygen is more electronegative, you want that to be your negative charge. So you might disconnect here where the oxygen is a minus. This whole group now is drawn there as a minus charge. And then you might think of a carbocation. Now, does that carbocation, can that carbocation even exist? No, that's why it's imaginary. Okay, but this plus charge leads you back even further to real reagents that you could use, i.e. alkyl bromides. You see the things we can do with alkyl bromides. And this minus charge looks very reasonable. If you put a sodium plus, that's a real molecule. Okay, that's sodium isopropoxide. So we know we can do this, SN2. Okay, so that's one possibility. So these, the bottom ones, are the real reagents. These synthons are imaginary. So B, we can disconnect. And what do? We want the oxygen to have the minus charge. Oops. And the carbon to have the plus charge. Now that looks a little bit more like a realistic carbocation. Again, you could put a sodium here. Those are the synthons. This is the real reagent. The real reagent for this is still a bromide. Your carbocation is never a real reagent. Okay. Now, this is again a review of SN2, SN1. What do SN2 reactions favor, or what favors SN2? Primary alkyl bromides, or special primary. This is a secondary. Okay, you get a strong base and a secondary, then you have a chance of doing beta elimination. Okay, if you did this pathway B, you would get more elimination products. You'd get some elimination products most likely. Here, this is going to be a much cleaner reaction. We can make this from the alcohol. If you wanted to go back further, you can make that from the alcohol, isopropyl alcohol, okay, with sodium hydride. We haven't shown that yet. We'll get to it. That's just a mention, look ahead. So there's a good way and a better way to disconnect or to work backwards to do a retrosynthesis for this molecule. Okay, again, using our knowledge of SN2 and what it prefers, that helps us to synthesize molecules. Let's look at some more prep. Again, some more review. We have a primary alkyl iodide. Sodium isopropoxide, strong nucleophile, also a strong base, but we've got a primary, so it's going to prefer SN2 if it's got a strong nucleophile. SN2. Oxygen-carbon bond forms, ether. Okay. Ether products, so preparation of ethers. I'll give you another one to take home. It's very similar. Sodium ethoxide, an ethyl group, sodium ethoxide. What does that give? Work through that problem. sodium hydroxide, strong nucleophile, primary, SN2, alcohol. Okay, so that's an alcohol. That's a way we can make alcohols. We can make ethers. Let's give you another take-home example. With sodium hydroxide. Now we've got a secondary. I'm asking for substitution products here. We've got a secondary and a strong nucleophile. So what's going to happen? Fill in the blank there. Remember, the key term is inversion. Okay. Same starting material, sodium methoxide. Same principle. Draw the product and inversion. Okay. So how do we make these alkoxides? We've shown a lot of them. I hinted at it. How to make alkoxides are, I'm going to pick one way. There's more than one way. You start with an alcohol and you deprotonate. Use a reagent called sodium hydride. It's a strong base. And you get sodium alkoxide. Again, you don't need to know the names, but the byproduct is H2, hydrogen gas. pKa of H2 is 35. pKa of alcohols is about 16. 10 to the 20th, give or take, more acidic. Okay, so this is a strong base. Again, this is essentially an equilibrium problem. You're comparing two acids. And I've given you the pKa's, but if you wanted, you could think about the element effect. Okay? A way we can think about sodium hydride is this. This is an introduction to this concept of hydride. So hydrogen and carbon have similar electronegativity, right? So this is just an example of the electronegativity effect. Okay? That's a better base. Hydride is a stronger base than RO minus. Okay? So you're comparing this base and that base. Recall the electronegativity effect, right? Oxygen's much more electronegative than carbon, and therefore it's much happier to have a negative charge, so it's weaker, more stable. A carbanion is a better base. Hydrogen and carbon are similar electronegativity, therefore they are similar base strengths, and H minus with a pair of electrons, hydride, is a pretty strong base. Okay, so again, we can use the electronegativity or element effect to understand acid-base chemistry. So essentially, we're going to treat sodium hydride like this. Okay, it's more complicated than that probably. Sometimes people draw it like this. They actually draw a bond. Okay, and you know, it's either way is fine. Okay, but it's a good base. So that's preparation of alkoxides. We've been seeing that as those as nucleophiles, etc. Now let's look at epoxide synthesis. And this is a twist on SN2. We have kind of a special alkyl halide with an alcohol attached to it. Put some stereochemistry there. It's called a bromohydrin. The name doesn't matter. But what can happen? Sodium hydride. I give you this reagent, right? You work through it and you remember that it's this. The hydride can deprotonate. Right? I'll fill in the rest of the molecule. Nothing else has changed here. You've just deprotonated. I've got a sodium plus there. Everything else is the same. I'm going to abbreviate that as an ethyl, ET. Your methyl, H, bromide. Now, what does this look like if we covered up, again, this whole part of the molecule is the same. If that was just a CH3, it'd be a sodium methoxide. That's a good nucleophile. This here is a carbon-bromine bond. That's a good electrophile. What can happen? This O- comes in and attacks the carbon, kicks out the bromine. So it's SN2. SN2. It's going to come from the back side, and all this stereochemistry is sort of maintained. This doesn't change, this one here, and this is inverted. Okay, the CH3 and the hydrogen are going to kind of be pushed down. Let's draw that product. Okay, so we have deprotonation with sodium hydride, and we have intramolecular SN2. Intramolecular, same molecule. Intramolecular SN2 gives this epoxide. This is a trans epoxide. It's the one we talked about earlier in the naming. So let's look at general features, 9.7, general features of reactions. Right, we spent all of chapter 7 talking about nucleophilic substitution of alkyl halides, SN2 or SN1. Then we spent chapter 8 talking about base-mediated elimination of alkyl halides to give alkenes, and by E2 or E1, okay, driving off a molecule of HX. We talked about the alpha and the beta, so beta elimination. Okay. Now we can look at very similar types of chemistry with alcohols. A lot of this, the remainder of the chapter will focus on alcohols. We can do substitution. And we're going to see how we can then go to alkyl halides. So it's going to be the reverse of chapter 7. And then we can eliminate with alcohols using acid. We'll find both of these are kind of powered by acid. And we can form double bonds and drive off an equivalent of water. We're going to go through all these mechanisms as usual. OH is a poor leaving group. So in both of these cases, you're going to convert OH to H2O. You're going to protonate it and make it into a good leaving group. Okay. So we need very, very different conditions. Up here, nucleophiles and bases are both basic. Here, with alcohols, bases will deprotonate that H. That H is relatively acidic, so you would just deprotonate or give no reaction. Okay. However, we can activate, because of the nature of the alcohol and the lone pairs in the alcohol, we can activate the alcohol with acid. So if we used basic conditions in chapter 7 and 8, we're going to use acidic conditions in chapter 9, or a lot of them. And then we'll show some other reagents that work by other ways. Okay, so let's drive this point home. Recall this equilibrium. Alcohol plus HCl. Which way does the equilibrium lie? we know, again, HCl is one of the strongest acids you'll see. So just simply memorizing that, you can say the equilibrium lies to the right. pKa of this is -7. pKa of this is -2.5, somewhere around there. Okay, this is still very acidic. Protonated alcohol is still very acidic, but not as acidic as HCl. Again, this is the element effect, but it just is confusing a little bit because we're going from neutral to cation and anion. So it seems strange to have a plus and a minus, but this plus and minus has electrostatic interactions, and we're going to get this charge separation, this dissociation. Okay, so we know that can happen. Okay. So now, once we have our alcohol that is now protonated, we've created a good leaving group, whatever X may be. Dissociation. Now, water is a good leaving group. Not quite as good as X when it's bound to the carbon, but pretty good. Okay. So water is our fourth leaving group. Chloride, bromide, iodide, and water. We actually will have a fifth that we'll introduce to this chapter. And so you can either go substitution, and now X can be your nucleophile. The X minus that you've generated from the HCl or HBr or HI can push in there, kick out water, and you get substitution. Or you can have elimination, alpha, beta. Okay, so water is still leaving, but instead of substitution, you have something else picking off this proton, electrons coming in and giving you elimination. And your byproducts are going to be eventually like H3O plus, X minus. Okay, we're going to go through more mechanisms. Similarly, ethers can undergo the same kinds of reactions. We'll talk about those. Epoxides are different because they have ring strain. There's basic conditions that pop that open. We'll go over epoxides as well. Next lecture, we'll start with 9.8 and talk about dehydration of alcohols to alkenes. We'll get there in the next lecture. So this is the intro. So we'll see you next time. Talk to you.